This is a demo of Adaptive Computing's HPC Cloud on Demand Data Center, or ODDC product, which uses the extreme scale scientific software stack, or E4S Pro image, which is running on the Google Cloud platform. ODDC allows you to manage all aspects of deploying a cluster on a cloud platform. It provides a web interface, and it allows you to configure the cluster, upload your credentials, deploy a software stack, and then manage a cluster. Here is the cluster that we are running. It has 2 nodes. You can see the configuration. It has support for a job monitoring capabilities, a file manager, accounting. You can even check the instance prices and see what it costs for, say, the C3 standard 88 compute nodes in different regions of the world. So here I have a cluster manager. I can look at the cluster that I'm deploying. It's the E4S cluster. It comprises of 1 head node with N1 standard 8, and then 2 compute nodes, which are C3 standard 88, which feature the IPU network. So I'll launch a remote desktop by connecting to the VNC viewer like this, and then I can connect to it and get this screen. So once I configure this VNC session, I can launch a terminal, and you can pick from any of these applications. And here is the terminal. Let me just make this a little bigger and change the preferences. So I can change the custom font and say make it bigger and set it up. So this is 18 font size. Okay. And it has set up back in my home directory. Now, when you instantiate a cluster, there are many questions you may have. It can be a daunting task. Which image should I pick? Will it have all the software that I need? How should I configure it? For Google Cloud, do I need to use the Google Cloud Console, or should I install tools like GHPC and gcloud on my desktop and then create some YAML file to accurately describe the properties of the cluster? Should I use commands like gcloud to configure the project, GHPC to create and deploy the cluster? Will I choose the operating system image appropriately? Will it have the packages for AI/ML and HPC? Will it have drivers for efficient internode and intranode communication? What about the remote desktop environment like this, so I can launch GUI tools? And will the nodes that I get, will they be close to each other? Do I need to worry about placement policy so the nodes are close to each other using a compact placement policy to reduce that network latency between the nodes? Will it support the IPUs, the network adapters that I need for low latency communication? So the E4S Pro image provides all of these packages for HPC and AI. And let's just start up this image and look at some AI packages. So I'll go to the examples directory here, and let me just go to, say, TensorFlow. TensorFlow is a framework that makes it easy for you to build and deploy machine learning models. I have a simple TensorFlow program over here, and the Python that we ship in this image has the AI/ML tools already installed in it. So you'll find tools like TensorFlow, PyTorch, JAX, and other tools like Horovod, LBAN in this image. Let me just run this with Python, and I'll be able to validate that TensorFlow is correctly installed on this system. Now I have two nodes. These are compute nodes that are available here. Let me just open up another terminal, show you etc hosts. The names of the two nodes are these. And we'll use this in our examples. So here is the run.sh that just ran. Let me go to the PyTorch example. Cat run.sh f4.py. This is the example that I'll be running. PyTorch is a fully featured framework for building deep learning models based on the Torch library. It's used for applications such as computer vision and natural language processing. JAX is another important AI framework. And here is the run.sh script. And here is the JAX simple. It's using Torch in this case. And let me run this example. And you can see the output here. Now, all of these Python-based tools are accessible through the Jupyter interface as well. And I can launch a Jupyter notebook and access these tools. I'll launch a terminal command for looking at the different Python tools that we have. So I can say Python, say import TensorFlow, import Torch, import JAX, import matplotlib. And most of the commonly used packages like NumPy or SciPy, they're all there. Here is the output of our JAX program. Let me just go over to a Jupyter notebook, say matplotlib example, and I can just say Jupyter notebook. Now this is where the GUI capabilities of this remote desktop running on VNC are seen. So here is the Jupyter notebook, and it will launch a web browser. And it's loading up. I can just say, click here and say, create a new notebook. Let me just run some Python code in it. And hit Shift Enter. And then it will be able to run this. And you can see the image over here. So you can launch these notebooks. There are other graphical user interfaces and other tools that we have here. Let me just show you the tau performance system. I have paraprof in my path. And let me just load up a PPK file. Tau is a profiling and tracing toolkit. We can measure the performance of an application Here, let me just change the preferences and make it a little bigger font and make it say bold, apply. So it shows me all of these nodes, which are MPI ranks. I can click on a node and see which functions are running on that. I can open up a 3D visualizer. And here I can see the bar plot and see the shape of a profile. Here I can zoom in and see the 256 MPI ranks and the functions and the time spent in each of these functions. So I can see that the shape of this function and this function is kind of inverse of each other. I can even create a crosshair and look at the performance of individual functions. I see a little spike over here. So I can just let me go over here. And see the function here and evaluate where the two threads intersect. So here, where the two crosshairs intersect, I can see that on rank 199, the time taken in this function was 129.5 seconds. And so this is a simulation of a tokamak reactor, and the CPU that gets the central access has to do more work. So it's different from the rest of the MPI ranks. I can look at a scatter plot, and you can see that between 31 seconds and 260 seconds were spent in MPI barrier. You can see the three different functions over here that represent the most standard deviation. And each rank has a unique value for these three functions and the color function. And so we can draw these balls and see the clustering of the profile. And there is this one central axis rank, which is different from all the rest. And then you can see that these two functions are inversely related to each other. The coefficient for correlation is -1. You can see topology plots, triangle meshes, bar plots, and you can look at other tools that we have in this. I have visit and also ParaView. So let's look at visit. I can say visit. So this remote desktop environment offered by VNC allows us to launch all these tools. Let me open up a file here, example.silo, add a pseudo color pressure, and then draw it. And then you can see the 3D graphics provided by this visit tool. I can say add a slicing operator with iso surface and then draw it. And you can see the 3D graphics all running on the Google Cloud. Here is another example of a GUI tool. This is a Nalu wind program's output, and I can say para view output.e. And Nalu wind is a low Mach number CFD package from Sandia and NREL, and it is used for simulating the turbines of the blades of a turbine, the airflow around this. And you can see there is the output. Let me just apply. I can see how a fluid flowing over a plate is simulated here. Let me choose this surface to surface with edges. And I can examine this. I can look at the pressure and see the pressure from the simulation. The point Gaussian. Or I could just load some other examples. Sorry. It comes with some standard examples. Is the example visualization. And there are a number of these examples here. And you can see the performance of the GUI tools within the cloud environment here. So here's a clip one. Let me show you the MPI examples. We have a cluster, and as I mentioned, it has these two nodes. I can, of course, SSH to this node or send a command and say ls CPU, see how many cores it has. And you can see it has an Intel Xeon Platinum processor. We're looking at 44 cores per socket, 88 cores total with the hyperthreading, 2 threads per core. And they are connected by the IPU network. So I'll need to build this simple example. I have MPI TC in my path and compile.sh. So this MPI proc name example is built. I can, of course, run it on the head node here by just saying MPI proc name, and it will run it on the local Ubuntu host. But I want to run it on the compute nodes, and so I have this run ODDC.sh where I'm just taking the last two Nodus hosts and putting them in the hosts.txt. So is there a hosts.txt? Okay, so I'll run ODDC.sh and it will create this, add it, and now it's running over here. When I say MPI run with 2 MPI ranks, 1 process per node with this host file that I just created. And then it has the IP addresses and it's running on these 2 nodes. So one of the important things in deploying a cluster is seeing the latency between the 2 nodes and the bandwidth. So if I have latency, I can say run ODDC latency.sh, run ODDC latency.sh, and now it will use the host file that I have created and then launch this OSU latency in the nodes. And you can see that it's getting 17 microseconds using the IPU between the nodes. And if I say run ODDC bandwidth.sh, then run ODDC bw.sh. So that is 3.5, as much as 3676.29 or nearly 30 Gbps that we are getting between the 2 nodes. The peak value for H3, I believe, is 200 Gbps node per node between the nodes. Here is a benchmark for the NAS parallel benchmark. Let's go to NPB 3.1 and let's say clean.sh, compile.sh, and let's build the LU benchmark and launch a 32 MPI ranks between the 2 nodes. Okay, so we have built a 16 MPI rank example. Run ODDC.sh, and we are using 8 ranks per node. And it's using the torque scheduler. We are running this on the 2 nodes, 16 ranks. Now, if I wanted to measure the performance of this application, I could use the tau performance system, which I mentioned is the profiling and tracing toolkit, which is also integrated as part of E4S. So let's see how long it takes to run. It takes about 32.98 seconds. If I want to run it with run tau ODDC.sh, the only change I have to make is to add the tau exec with the event-based sampling parameter. And then we can launch paraprof and view the profiles. So run tau ODDC.sh. And we'll see the total time taken now. With tau, it will run a little slower than it did with without the instrumentation. Here, it took 32.55 seconds with tau, and earlier it took 32.98 without tau. So the perturbation is negligible, but you can see the 16 MPI ranks here. And you can see the set statistics table, see how much time was spent in the application. You can see the time spent in MPI receive and what it internally was doing. Here is the time spent in the application. And see the distinct functions. 7.4 seconds were spent in the RHS routine on MPI rank 0. And you can see the line numbers. Say 1 second was spent in line 339. I can see the source code, where it is spending this time. And you can see the do loops in Fortran. You can see 1, 2 levels of nesting over here in this function. And here are the different loops where it's spending time. So you can see all the functions. There was no change to the application binary, and you can see the time spent in various application routines, and see the overall profile for each rank. So with this, you can also see pprof to look at the performance of the application with a text-based browser. Let me look at a PETSc example. Now, in this example, I'm using a solver. And you can see how to run this application. I can say clean.sh. It uses the Spack package manager. I can cat the compile.sh and then compile this program, EX50. And you can see all the libraries that it needs are coming from this E4S distribution. I can say Spack find PETSc, and it will show me the PETSc package that is installed. Now here, I can say run ODDC.sh, run ODDC.sh, maybe say run tau ODDC.sh. And in addition to this tau exec-ebs, I have this log perf stubs. And let me just add some tau environment variables. I can say tau call path equals 1, for tau call path depth equals 100. Even set, say, number of threads to be, say, 16. And say run tau oddc.sh. And it will run this application, run it on the 2 nodes. And then we'll see the output with paraprof. And now you can see the time spent in this MATLU factor routine and the full call path. You can expand this thread statistics table and see where the 10 seconds were spent. The main stage calling PC setup, which calls MATLU factor, and the names of the functions that were called within this, the samples that were taken. And other functions, and the full call path is exposed. KSP solve is calling PC apply, which calls mat solve, mat mult, and so on. So we can instrument the code quite easily with Tau. Let's look at Quantum Espresso. So Quantum Espresso is an electronic structure calculation program, and I can say run ODDC.sh. Let me maybe run this on, say, 32 MPI ranks and put 16 of them on each of these nodes. And say export OMP num threads to be, say, 2. Run ODDC.sh, and it will load the Quantum Espresso package using Spack, and there it runs the code. Now, we have a number of packages that are provided. I showed some AIML packages. Here are over 100 different packages that Spack is used to install. And it includes tools like Hive, which is a data analytics package. And it includes LAMMPS here, and even, say, PAPI, OpenFOAM. We can look at this OpenFOAM, and also other numerical libraries from Trilinos and Cocos and Raja. So let's go to LAMMPS, and here is a run ODDC.sh script. I'm saying run ODDC.sh, and I'm launching the LMP executable. Setting number of threads as 2, doing a Spack load LAMMPS, and then running it on 32 MPI ranks on the 2 nodes. And there it is. Is the output of the code. You can see the output. LAMMPS is a large-scale atomic, molecular, massively parallel simulator. It's a classical molecular dynamics simulator from Sandia National Labs. OpenFOAM is a leading open source software for computational fluid dynamics, or CFD, and it has an extensive range of features to solve anything from complex fluid flows involving chemical reactions, turbulence and heat transfer, to acoustics, even solid mechanics and electromagnetics. So here is a cavity example, and here is the run.sh, and I'm going to run this cavity and then launch ParaFoam. So it's running all of these, and then in the cavity it will launch this. You can see over here, I can go down to the surface with edges. There's the pressure. Let me apply this. So there is the ParaFoam based on ParaView, the viewer that we had seen earlier. So it's possible to launch the jobs on multiple compute nodes using ODDC we are able to have a remote desktop environment, launch these tools, AIML and HPC tools, and see the output, visualize it. Now, there are several issues when you deploy a cluster like this. You need to make sure that the image that you use has efficient intra-node as well as inter-node communication libraries, that it has the modules that are needed. Here is, for example, the XPMEM kernel module. So unlike the SHMEM, which allows other processes to access newly allocated memory, XPMEM allows accessing any existing data. And so it allows for a more efficient intra-node communication, because the send buffer content can directly be copied to the receiver, the receive buffer. And so for intra-node communication, XPMEM is important. And we have built a full software stack based on these libraries. So you can see these are over 100 packages that have been built. And you can say Spack find to show you all the packages that are in this. And so over 800 packages have been installed using Spack. You can see all the specs over here. I can say Spack find -- loaded. I have not loaded a package here. I can say, for example, if I were looking for PAPI avail, it's not in my path. I can say Spack find PAPI. It's there, so I can say Spack load PAPI, and then I'll have PAPI avail in my path. And I'll be able to see which hardware performance counters I can use with packages like tau. And I can measure all of these hardware performance counters which are available. Say L1 DCM is available on the chip here, but L2 DCM is not available. Then I can look at some other applications and some other languages as well. So we have Julia over here, examples, demo, Julia. Here is a Mandelbrot example, just taken from this rosettacode.org. And I can just say run.sh, run.sh. And there's the output. So Julia is available. If I say Spack find Rust, then Rust is installed. So I can say Spack load Rust. Spack find -- loaded. And I can see PAPI and Rust are now loaded in my environment, which Rust C -- version. So what is interesting about this is that in the Spack opt directory, we have a number of these packages that are available. Over 800 packages. Some of them have different versions. Say Spack find SuperLU-dist. So there are two versions. It shows you that SuperLU-dist has 7.2 and 8.12 version available. If I say Spack show me the dependency listing, show me the variants of SuperLU-dist so I can compare these. And then I can see this is the hash, the 7-digit hash, and this is the SuperLU-dist 7.2. And it uses all of these packages with MVAPICH, and then SuperLU-dist over here, 8.1.2, and the variants. And if I wanted to look at a particular location, I could even use this hash over here and say Spack location -I, and then you can find out more about Spack at the spack.io webpage. They have a tutorial. You can learn more about E4S at the E4S.io location. Here is the directory. I can look at the lib directory and see libparmetis.so is installed over here. If I wanted to try this example, SuperLU-dist CPU, I can say clean.sh, cat compile.sh, where I'm locating the SuperLU-dist, and say compile.sh. And I've asked for SuperLU-dist 8 or better over here. And then I have the PD drive executable here. So when I run it with run ODDC.sh, I can do that, or even on a single node.sh. And there is the output of this example. So we can see a number of other test cases in the demo validation test suite, which is the validation test suite for the E4S package. You can see all of these programs where you can run the examples. So in short, the extreme scale scientific software stack provides AI/ML packages. It has TensorFlow, it has PyTorch, it has Horovod, it has LBAN. Here is a f7.py. And it's using TensorFlow internally. And you can use all of these packages together with a common Python installation. And here's the output of Horovod with TensorFlow. So if you're looking for an image to deploy on the Google Cloud Platform, the E4S Pro image available through ODDC provides a single remote desktop environment which has MPI configured with different HPC and AI/ML tools all available within the same image. And as it's running, I can start up another terminal and show you what you can do with Spack. So I mentioned that we have over 800 packages installed. But what if you want another package which is not available through this E4S installation? Say you were looking for which Valgrind, for example. Now, if I say Spack find Valgrind, it's not installed, but if I say Spack info Valgrind, it shows me that it's available to install. Now Spack install Valgrind will install this, not, Valgrind. It will install it not in the read-only partition of /Spack, but it will install it in my home directory, which will be mounted on the compute nodes. So you will be able to expand the set of packages that are available in this distribution by using the Spack command. And it will use up the dependencies that it finds in the list of packages that are already installed. So here is the output of the program while it's running on the head node on Horovod, and I'm running the Valgrind installer over here. Maybe I should have installed it. Okay, here it's installing it. You can see that it already found all these other packages like bzip2 or MVAPICH or xz in the /Spack directory. And it is reading those packages, and it's then installing this Valgrind. So all its dependencies are satisfied by using the packages that are installed in the /Spack directory, and it then installs it in the home so that it will be possible for the compute nodes to see this, and you can have a union of both of these sets of packages which are installed in the read-only file system as well as in the read-write file system on the home directory. So it's configuring it, and it will install the tools from source. So it downloads it, and it will take care of that. So it's building it now. And to use Valgrind, I'll just have to say Spack load Valgrind. And let's see. Yes, the Horovod is running as well. So what I want to end this with is the fact that with this E4S Pro image, you can easily deploy the cluster using ODDC. And ODDC also allows you to have a dashboard. You can see the ODDC console here. I can say notice commands in this terminal window. Notice cluster SSH --admin E4S GCP. This is the cluster that we used over here, E4S GCP. And I can say notice cluster :SSH --admin E4S GCP. And then I can log into this as the Ubuntu login, which has the ability to do sudo bash and get root access. And then we can also have Spack installed over here. So it allows you to access super user credentials over here, installing it here. And so who am I? I'm root over here on the login node. And of course, our VNC session is showing me that Valgrind is now installed in my home directory. I can say Spack load Valgrind. Which Valgrind? Valgrind -- help. And you can see that this tool is working now. And this is nearly complete for the Horovod run. So to see what packages we have now after this installation, I say Spack find, it will show me all of this 874 packages. And I can see Valgrind listed over here that we just installed. What you can also extend this environment with is containers. And we have a Singularity, which is installed over here in this image. Singularity 4 is installed over here. And you can choose some images. For example, from the extreme scale scientific software stack page, you can go to the download section and pick images, such as the one API x86-64 image or the AMD or other images. This is the E4S 23.11 release. We have full-featured GPU images. There are base images, minimal Spack images at Docker Hub, as well as at our site. And you can click on this Docker link and it can show you the images. So, for example, this has over 100,000 downloads. And you can see the CI images and other documentation for bare metal installation of E4S or the use in ODDC. So to sum up, I can log into clusters. I can deploy clusters, configure them, use my credentials manager, create a software stack. I can deploy the cluster, accounting, file manager, monitoring the jobs, and see the current prices for the different nodes. And then even deploy or destroy the cluster. So if I wanted to destroy it, I can just use this and click it, and that will kill the cluster. And it's destroying it. So HPC Cloud on Demand Data Center provides all these capabilities through a web interface. So instead of using some scripts, I can do all the cluster deployment and configuration activities through a web interface. I hope you found this useful. Please get in touch with us if you would like us to customize any solution for using E4S on ODDC. Thank you.